Welcome to Empowered Learning. This is the fourth video in the video series on moments and finding center of mass for an object by using definite intervals. So in the part 3 video, just in case you haven't watched it, I went over several examples of finding the center of mass of a two-dimensional figure, mainly a thin plate. For most of those problems, our plate was defined as some region that was bounded either above or below by some function, f of x or f of y. And of course, on the other end, let's say if I bounded it on top by a function f of x, then it means on bottom it was bounded by the x-axis. And so when we had our plate being bounded as a function of y on top, then the y-axis would be what the bottom of the plate would be. So needless to say here, we only had one real function to deal with to figure out the lengths of the sample strips that we were going to use, whether we were using horizontal ones or vertical ones. And we also only had one function to really deal with if we were going to find the centroid for the sample strip. Now, in this video, we're going to look at some instances to where our plate is going to be defined as being in between two functions, okay? So all the same stuff applies, but let's say, for instance, like in figure F, that we have a situation here where our plate is going to look like what you see here. So let's say we have a plate and it's bounded on this side by x equals a and x equals b here. But of course, the top of the plate is going to look like f of x, bottom of the plate is going to look like g of x. So in those instances, we would have to consider both functions in modeling what this particular sample strip would look like, okay? And so the only difference here is that and in this case, I'm using a vertical strip so that I know that my x tilde, which is the x coordinate for the centroid for this sample strip here, is just going to be a random x value. But now y tilde, which is the y coordinate for the centroid for the sample strip, is going to be the average of these two functions here, which is just basically f of x plus g of x divided by 2. So I've written it this way. We know that the length of the strip is really the difference in between those two functions. And of course, the width of the strip will stay the same at dx. The area of the sample strip will just be the product of the length and the width. And of course, the mass, or the differential mass of the sample strip, is going to be the density times the area, which is just, again, the difference in between those two functions times dx. And so in that makes our formulas for the moment about the y-axis, moment about the x-axis, look a little different, okay? Now, of course, the general form is still the same. The moment about the y is going to be the integral of x tilde dm. It's just that x tilde and dm may look a little different. And particularly for the moment about the y, the dm part looks different. For the moment about the x, it's integral of y tilde dm. And of course, our y tilde, again, is just the sum of f and g divided by 2. And dm is going to be this density times the difference in between those two functions. And of course, all that is multiplied by the differential width of the sample strip, which is dx. And of course here, one of the things that we note is that since I have f plus g here times f minus g, I know that I can multiply that together and get f squared minus g squared, okay? And then of course, here the x coordinate for the centroid is still the moment about y divided by m, and the y coordinate for the centroid is going to be the moment about x divided by m, where m is your system mass. And if you remember, that's just going to be integral of dm, whatever that is. And of course, all of these, even though I haven't written it here, will actually have limits of integration going from A to B. So this will follow suit. All right, so with that being said, that's the only thing that's really different here. So we're going to look at a few examples to where we actually have to sketch the graph of multiple functions and then figure out how to model the sample strip by using two functions instead of just one. All right, so before we do that, I just wanted to also show you what it looks like whenever we model things using the horizontal strip. And again, the center of mass for the sample strip, if it's horizontal, the y value just remains random, whereas the x tilde here is going to be, of course, the sum of the functions defined in terms of y divided by 2. Length of the strip is still the same. The width is now going to be dy instead of dx. And of course, everything else just kind of follows suit here. And so you see that pretty much looks the same. Again, everything that is just defined in terms of y instead of in terms of x. All right, so for this example, we want to find the center of mass of a thin plate of constant density. So that means density is really not going to play a role here, but we'll keep it in and see that it will eventually reduce itself to 1 and get removed from the problem. We want to do this by constant density covering the region bounded by a parabola and the line y equals 12. Okay, and so you see we have the line y equals 12 here, parabola here. So this line y equals 12 is here. And of course, our parabola, I'll draw that in a different color, will be here. And so our plate is going to be the shape. It's going to look something like this. Basically going to look like this, okay, like a shield. And so what we want to do is figure out, well, what's going to be the center of mass of that shield by looking at some sample strips, okay? Now, the first thing that we note here is that since this shape here, this thin plate, is going to be symmetric about the y-axis, we know that the x-coordinate for the centroid, or the center of mass, can be on the y-axis. Okay, so because of that, we know by definition that x is going to be 0, or the x bar is going to be 0 there. Okay, so that cuts down on the amount of work that we need to do. And if you remember, x bar is just going to be the moment about y divided by m. So what this tells us here is that we no longer need to figure out what the moment about the y-axis is. Okay, the only thing that we do need to find out now is what y bar is, which is the moment about x divided by the system mass. Okay, so we've cut down our work some by noting the symmetry properties of the shape that we have. All right, so the next thing that we need to do here is, since we know that we need the area bounded by these two functions here, we need to figure out where they intersect. And that is essentially just letting us know that 3x squared is going to equal 12. And of course, we see that those two functions intersect at x equals plus or minus 2. So that's going to let us know where our limits of integration come from. So this will be our A and that will be our B. So after we have that, we could model this using vertical strips or horizontal strips. But as you see, since both functions I was giving are actually functions of x, it's easier for me to model with a vertical strip. Okay. And so that's the statement that I'm making here. Since we're modeling this thin plate area with vertical strips and the thin plate area is bounded between two curves, then we need to sort of model what this sample strip is going to be accordingly. Okay, so if you remember the center of mass, since I have a vertical strip, my x tilde is just going to be random x value. My y tilde is going to be the average of these two functions, which is just 3x squared plus 12, all that divided by 2. And so you see that I have that here. So the length of the strip is just going to be the difference in between the two functions. So 12 minus 3x squared. And we write it as 12 minus 3x squared instead of 3x squared minus 12, because from x equals -2 to x equals 2, this horizontal line y equals 12 is above or equal to the parabola y equals 3x squared. So that's why we write the 12 first. Okay. Now the width of the strip, since we have vertical strips, is always just going to be dx. The area of the strip is going to be just the length times the width of the strip. And of course, the differential mass is just going to be, or the mass of the strip, I should say, is just going to be density times whatever this differential area is, which again is just going to be the length here times the width there. Okay. And so noting that we only need to find out what the y coordinate for the centroid is by knowing what the moment about the x-axis is and what the system mass is. And of course, I have those definite integrals to find there. We can just plug everything in and go to work. Okay. So if we see here that once we actually plug in the y tilde and the dm, so all of this is the y tilde, this is the dm part, then it's just a matter of rearranging everything and making it look nice so that we can actually do what we need to do with it. Okay. So of course here the delta here, which is representative of the density, that's a constant, so we just pull it out. And here we have 12 plus 3x squared times 12 minus 3x squared, which we know that's just going to be 12 squared minus 3x squared squared. Okay. And we end up getting 144 minus 9x raised to the fourth. And then from there, we just take the antiderivative of both terms. We evaluate at 2 first. So we plug in 2 everywhere where we see x, minus, and then we plug in 0, and you can barely see it here, but I got 0 there. And we know that if we plug in 0 for both this x and this x, everything is just going to go to 0. Okay. So with that being said, we know that all we have to do is just work on what is right here, which ends up being 288 minus 288 divided by 5. And then at that point, I try to rewrite this to make it look a little bit nicer. And we see that we end up with this expression here, which is just 1152 over 5 times the density. Okay. Now for the system mass, again, all we do is just take what dm was, which was all of this business here. Because remember, dm was all of this. And we just plop that in, factor out our constants, and then take the antiderivative of what's left. So take the antiderivative of 12, take the antiderivative of minus 3x squared, and then after that, evaluate at 2 and evaluate at 0. And of course, the reason I'm doing that here is because if you notice, this particular function here is an even function. Okay. And of course, the same kind of thing happened here when I went from here to here. So I noticed that whatever function I was dealing with was even. So I used that integration property that says that, hey, if I'm evaluating the definite integral of a function, and I'll write it here. I'm evaluating definite integral of a function like this, and my function is even, then I could rewrite it this way. Okay. So I got lucky here where both of my functions ended up being even, so it made doing the integration a little bit easier to do once I write it into this alternative form. So again, from here, once I take the antiderivative and evaluate at 2 and then evaluate at 0, we see that we just get 32 times delta here. So that's what's showing right here. So now all I have to do is just take y bar, which is moment about x, divided by the system mass, and I see that I get 36 over 5. And since we already said that x bar was going to be 0, since the thin plate was symmetrical about the y-axis, we already know that the x-coordinate for the centroid is 0, y-coordinate is 36 over 5. Okay, so for our next example, kind of the same thing, but this time a little bit more interesting because we don't have a horizontal line that we're dealing with as one of the functions. We actually have a line that has a negative slope. So we want to find the center of mass of a thin plate of constant density covered by the region bounded by these two functions here. Okay, and so what I did is I sketched a graph of what 3x minus x squared and what y equals minus 3x would actually look like. And we see here that both of those functions will intersect each other at specific points. And all we have to do to find out where those points are, those x values are, is to just set them equal to each other. So that's what I did here. And when we do that, of course, solving that quadratic equation lets me know that these two functions will intersect each other at x equals 0 and x equals 6. And so just to be clear here, we know that the shape of our thin plate is going to take on the shape of this parabola here. Take on the shape of this parabola here. And then on bottom is going to take on the shape of minus 3x. So that's what our thin plate is going to look like. Again, both functions are defined in terms of x. So it's better for us to model the vertical sample strip, well, the sample strip that we want vertically, okay? And of course, whenever we have vertical sample strips, we know that our x tilde is just going to be a random x value. So we just put x there. Y tilde is going to be the average of the two functions. The length of the strip is just going to be the difference in between those two functions. The width is going to be dx as always. And then, of course, the differential area here is going to be the length of the strip times the width of the strip, which we see here. And the mass of the strip, which we'll call the differential mass, is going to be density times this differential area, or the area of the strip here. Okay. And so, of course, our formulas for the moment about y, which is integral of x tilde dm, moment about x, which is integral of y tilde dm, and system mass, which is integral of dm, all stay the same. And so all we have to do at this point is just work things out. So the moment about the y-axis, we have x tilde dm. If you remember here, x tilde is just x. dm is all of this. So we just put that together. And then from there, we factor out this constant, which is going to be what our density is, and then we just take the antiderivative of what's left. So taking the antiderivative gives us what we have here. Simplifying that will just give us 2x cubed minus 1/4 times x to the fourth, and we evaluate that from 0 to 6, plugging in 6 first, in for x, minus, and then plugging in 0. And of course, with it being 0, plugging 0 in both terms for the antiderivative is actually going to end up being 0. So all we have to do is worry about this part, the first part there. So from that point, what I did here is, since I had 6 raised to the 3 here and 6 raised to the 4, I knew that both terms here had a common 6 raised to the 3 in it, so I factored that out. And I'm going to figure out what the rest of this is. And I see that the, what is it, 2 minus basically 6 over 4 or 3 over 2 just ends up being 1/2. And I know that 6 raised to 3 ends up being 216. And so half of 216 is 108. So the moment about the y-axis just ends up being 108 times the density. If we do similar thing for moment about the x-axis, it's going to be y tilde dm. And if you remember, all of this is what dm is. So this lets you know that y tilde is this part. Put that in, and we factor out the negative little delta divided negative little delta divided by 2. We have this remaining, the 6x cubed minus x raised to the 4. And so then we just take the antiderivative and evaluate at 6 minus evaluate at 0. And of course, we do all that arithmetic, and we'll see that we end up with a negative 1,296 over 2 times delta times this 3/10 here. And put that in decimal form, it would just be a negative 194.4. Okay. So lastly, we have the system mass, which is just the integral from 0 to 6 of dm. And again, may not have mentioned this clearly before, but we're integrated from 0 to 6 because that is where the x values for the point where the area is bounded by both functions there. Okay. So we just plug in what dm is, which is all this business. We can ignore this constant here, which is the density. Take the antiderivative of the first of those other two terms, and then after that, just evaluate using the net change theorem. And we see that once we're done with all that, we end up getting 36 delta. And so now the x coordinate for the centroid is just the moment about the y divided by the system mass. And we see that that's just 108 delta minus 36 delta, which gives us 3. And we also see that the y coordinate for the moment about, the y coordinate for the centroid is going to equal to the moment about the x-axis divided by the system mass. And we see that we end up getting a negative 27 over 5 for that. And so that lets us know where our centroid or our center of mass is going to be at. Okay, so for our next example, we want to find the centroid of a thin plate bounded by the graphs of the functions g of x, which is x squared times x minus 1, all that plus 2, and the parabola x squared plus 2. And here we're given that the density of this plate is going to be 4. And so we actually know what the density is, but at the end of the day, it really doesn't matter what it is. We know that it is constant, so therefore it's really not going to play a huge role in our calculations in the long run. Okay, so here we want the thin plate that's bounded by these two functions here. So what this is going to look like is we're going to have a plate that kind of looks like this. Okay. And so the first thing that we need to do is find out where the two functions intersect so that we'll know what our limits of integration is going to be. So of course, we can see here that both of these functions will intersect each other at the x-axis. That was just in sketching a graph of it, you'll probably see that. But the other thing that we don't know is this particular point here. Where will those two functions intersect on the other side? Now, of course, if we just set the two functions equal to each other, like how I've done here, we'll see that in solving this equation that we'll find that x either is going to equal 0 or x is equal to 2. And so that's where our limits of integration will be. Okay. And so because of that, again, our plate will look like what you see here. And what I've drawn here is a sample strip, and of course it's going to be vertical because our functions were defined in terms of x. So it makes it easy for us to model with vertical strips. So now we just need to remember what is going to be our x tilde, y tilde, which is the x coordinate and y coordinate for the centroid for the sample strip, the length and width of the sample strip. And then from that, we can get the area of the sample strip and what the mass of the sample strip will be. Okay, so we'll come back up here and talk about that. So for vertical strips, we always know that the x coordinate will be x coordinate for the sample strip will just be a random x value. Y coordinate for the centroid of the sample strip would just be the average of the two functions. And of course, you see I've done the work there. The width of the sample strip is going to be dx, and that's always the case. The length of the sample strip is going to be the difference in between those two functions. And so we take the difference of f and g, and we see this is what we get. And here we are again doing f minus g instead of g minus f. So we're doing this because we see that our parabola here is actually above our this cubic function that we have. Okay, so this function lies above this one for the x values where those two functions intersect. So that's why we have ordered it as f minus g instead of g minus f. So we won't have that. Of course, now that we have what x tilde and y tilde are, and the width and length of the sample strips, then of course the area of the sample strip is just going to be the length times the width of the strips, and the mass of the sample strip is just going to be our density times whatever the area of the sample strip is. And then from there is pretty much plug and chug from that point. So we find our moment about the y-axis is going to be integral of x tilde dm. And remember, since our two functions intersect each other at 0 and 2, that will be our limits of integration. So we substitute in what x tilde dm is going to be. And so, of course, all this is dm here. This is the delta part of that. And of course, x, that's what the x tilde is. And so then from there, it's just a matter of multiplying the x to both terms here and factoring out the 4, and then just taking the antiderivative of 2x cubed and x raised to the 4. And we get that here, and then everything else is pretty much you're evaluating it from 0 to 2. And we see that once we do all that, we end up getting 32 over 5. And yeah. So the moment about x is going to be integral of y tilde dm. All of this is our y tilde. And all that is our dm. And so once we do that, of course, this 4 and this 1/2 will factor out. And so 4 times 1/2 is 2. And now we need to multiply that x cubed plus 4 times 2x squared minus x cubed. So we multiply all that out in the next step. And then we take the antiderivative of each term of that result. And then, of course, evaluate from 0 to 2 once we clean everything up. So this step here I'm using to clean up. The next step, I actually plug in 2 everywhere I see x, minus, and then plug in 0 everywhere where I see x. And of course, every term ends up being 0 when I plug in 0. So I end up with moment about the x-axis being 352 divided by 21. Last thing that we need to do before we actually find the x and y coordinates for the centroid is figure out the system mass. And of course, the system mass, again, is just the integral from 0 to 2 of the mass of the sample strip, which is dm. So we put in what dm is, and then of course from there we just take the antiderivative of both terms, have this 4 factored out, evaluate at 2 minus evaluate at 0, and we get 16 over 3. And so now that we have that, we know that the moment about the y-axis is used to find out the x-coordinate for the centroid. And so we just have moment about the y divided by m, which is going to be 32 over 5 minus 16 over 3, which is 6/5. And the y-coordinate for the centroid is going to be the moment about the x-axis divided by the system mass, and that's going to be 352 divided by 21, all that divided by the other fraction, 16 over 3, which gives us 22 over 7. And so we see that this is our x-coordinate for the centroid, y-coordinate for the centroid. Okay. All right, so we're going to do one last example, and then we'll conclude this video and this video series. Okay, so for this last example, I'm kind of switching gears here, and we're actually going to talk about trying to find the center of mass of a thin homogeneous wire, meaning that the wire has a uniform density throughout. So this is technically a one-dimensional type of example, but because of the fact that I have a little bit of trig in it, I waited till the very end of this video series to kind of go over it. So what we want to do is essentially have a thin wire that has uniform density throughout, and it's bent like a semicircle. And what we want to do is find out what is going to be the center of mass for this particular wire. Okay, so in doing that, the first thing that we realize here is that we're dealing with a semicircle, and so by definition, a semicircle, the top half of it is a function. So that sort of kind of quiets our fears about, well, hey, you asked me to, find, we'll use something that isn't technically a function, but because of the fact that we're just using a semicircle, it is. If we had to use the entire circle, then it wouldn't be a function, and so we would have to find other ways to get around it. Okay. Now, here we also see that because of the fact that we know that this is a semicircle, that points on a semicircle are going to be the same as points on a circle. And if we have a semicircle of radius a, then that tells us that we also know what is going to be our corresponding points on this circle. And so what I've done here is, instead of using a sample strip, like a vertical one, a horizontal one, since we're technically dealing with a one-dimensional figure here, what we need to do is actually figure out a sample piece of our wire. Okay. And so to do that, we just need to figure out, well, theoretically, what is the smallest possible piece I could have, and what would be the centroid of that smallest piece? So to do this, the first thing I need to realize is that since this is going in the shape of a semicircle here, this is tied to arc length. Okay. And so we know that arc length is going to be radius times the angle. Okay. And so if I was to take the derivative of this arc length here with respect to theta, so let's say if I did ds over d theta, then that's going to be the derivative of this. And of course, we know that the derivative of any constant times theta with respect to theta is just going to be that constant, okay? Which in turn allows me to be able to say that the differential of the arc length could also be equal to r times d theta, okay? Now, in this case, since our r, which is our radius, is actually a, I could actually come here and erase R and put A in its place. Okay. And so from that, you see how I come up with this, the differential of the arc length, or the theoretical smallest piece that I could have there, is going to be of length A times d theta. Okay. So now for us to model this piece here and get all the information that we need, what I'm doing here is I'm actually using the two-dimensional formula that we would use for it. And I want to show you how we could actually use that and omit some of the parameters there so we can figure out what it is that we want. Okay. So here, the center of mass, still going to be the point x tilde y tilde. And of course, at any given point on the circle, we would have a point a cosine theta, a sine theta, depending upon what angle we're at. So this is valid. The length of the piece of wire makes sense for us to calculate since this is a one-dimensional figure. And of course, I've described how and why we do that right here. We're just taking arc length, taking the derivative of it and rearranging it. Okay. So this would be the length of the wire. Of course, the width of it, because of the fact this is one-dimensional figure, it doesn't make sense to calculate that. And again, since it's one-dimensional, it doesn't make sense to talk about area. Okay. Now, as far as the mass of this one-dimensional piece of wire, that would just be dm, which is just going to be our delta here, which is whatever the density is times ds in this case, because the only thing that we have to go by here is the actual length. And of course, that'll be just the density times the radius times d theta. And a note here that in this case, that our density is just going to be the mass divided by the unit length. Okay. And of course, here we know that the length of this piece is just going to be a times theta there. Okay. Well, just in general. And so I'm saying that because that kind of goes back to the whole arc length thing. Okay. Let me rewrite that. So here, when we're talking about density, we're talking about density of the entire wire, not just for that little small part. So that's why here we're saying mass. We're using big M here, which is the system mass, divided by the length of the mass, which is just going to be basically this length going from here to here, which will be a times theta, wherever, and we're assuming here that theta is going to be pi, and we'll put that into there later. Okay. All right. So now that we have that established, we can now find our moment about the x, find a moment about the y, and of course, one of these is going to be 0 just because of the fact that it's a one-dimensional figure. And then we'll figure out what our center of mass would be. And the only reason why we're going to do the center of mass as a point is because of the fact we have this particular wire sort of laying in a semicircle on a Cartesian plane. So that means we have a 2D plane that we're doing it on, so we're going to have to give the centroid in terms of both an x and a y coordinate. All right, so we know our angle could span from 0 degrees here to 180 degrees here. So we want to note that because that's also going to be our limits of integration. We know that, again, our density throughout the wire is just going to be the entire mass of the wire divided by the length of the entire wire, which in this case now is going to be the radius times the largest angle that we can have, which is 180 degrees, or pi if we put it in radians. So now that we have all that, we can now use that the x coordinate for the centroid is going to be the moment about the y divided by the system mass, where the moment about the y is still x tilde dm, integral of that from 0 to pi. Okay. And of course, our x tilde is just a cosine theta. Our dm is going to be the density times the radius times d theta. And we know that this density here and this A and that A are all constants. So we factor those out. And we see here that because of the fact that cosine is an odd function here, and we are integrating from 0 to pi, we know that that's going to end up being 0. Just from a graph standpoint, we know here cosine kind of looks like this from 0 to pi. And of course, the area that is above the x-axis is going to be the same as the area below the x-axis. So since we already know that, we know it's going to be 0, and it really doesn't matter what this is down here. So we don't worry about calculating that until the next step. All right, so for the next step, we have the y-coordinate for the centroid, and we see here that we're going to take the moment about the x. Let's try that again. Moment about the x-axis divided by the system mass. And of course, the system mass, or the mass of the entire wire, is just the sum of all these little small masses, dm. And of course, we know that dm was just A times delta times theta. The A and the delta are constants. Leave the d theta in here. So the antiderivative of 1 with respect to theta is just theta. Okay. In the numerator, we know that moment about the x is just integral of y tilde dm. Y tilde is just going to be the y coordinate for a point on that circle centered at the origin with a radius of a. And of course, dm again is delta times the radius a times d theta. We factor out the a, the delta, and the other a. All those are constants. And then we just deal with taking the antiderivative of sine. And here we know we need to work this out because if we look at the graph of sine, which looks like this, we know right here in the middle is pi, and we're actually just trying to find the area under the curve from 0 to pi. So we know that we're going to get something. So here we take the antiderivative of sine and we get minus cosine. We know that this a squared and a will just reduce to a, and those deltas there will reduce to 1. And then, of course, after that, let me erase this here. In the denominator, we're just going to evaluate theta from 0 to pi. Of course, plug in pi first and then 0 second. In the numerator, we know that we need to evaluate minus cosine theta from 0 to pi. Of course, we do all that via the net change theorem. Of course, cosine of pi is -1, so negative of a -1 is +1, and cosine of 0 is 1. So once we're done here, we see that our y-coordinate for the centroid is going to be based upon where or what our radius is. Okay, so it's basically going to be 2 times whatever the radius is divided by pi, and that is where the centroid for this particular wire will be. And so with this concludes this final example and the video series on using definite integrals to calculate moments and find center of mass of one-dimensional and two-dimensional objects.